Good morning. The Decarbonization Webinar, fifth in the series, is titled Oxy-Fuel Technologies with Different Hydrogen Carriers. It is organized by AIST's Decarbonization Subcommittee, a subcommittee of the Energy and Utilities Technical Committee. My name is Charlie Bender, and in a minute I will be introducing our presenters and our moderators. A few instructions for attendees. Our audio for each attendee has been disabled, but you can add questions to the question and answer feature at any time, which we encourage so that questions can be put to the presenters by our moderators. Our moderators will determine which questions are presented to the presenter, and this session is being recorded and will be available for an on-demand replay at AIST's website in about 2 weeks. Photos or recording of presentations is prohibited. And if you encounter technical difficulties during this webinar, please use the following email address, training@aist.org, for assistance on the technical problems. AIST has several guidelines which we freely use at every meeting and conference. There's an antitrust guideline with several statements, and in general, we are complying with the United States antitrust laws to minimize and eliminate any collusion between competitors. AIST also has an anti-harassment policy, and we'd like each of our meetings to be comfortable for attendees. In the end, if participants do not hold back any harassing behavior, then we may be asking them to leave the presentation. Again, if you have questions during the presentation, please submit them through the Q&A feature, which you'll find at the bottom of this screen. Already I see a couple of chat and questions, and I'll return to those once I introduce our moderator. Our first moderator is Ewan. Ewan is the Associate Director of Program Development with Linde. In this role, he is responsible for initiating new technology development efforts to help Linde customers reduce their costs and/or environmental impact through the use of industrial gases. Ewan has more than 30 years of experience in the development and commercialization of combustion technology for the steel industry, and he has authored or presented more than 50 technical papers and holds 4 patents. He is a graduate of McMaster University in Hamilton, Ontario, with a Bachelor of Mechanical Engineering, as well as a Master of Environmental Engineering. Ewan will introduce our presenters, as well as our next moderator, Mike Grant. And Mike has agreed to speak a little bit more about the Subcommittee on Decarbonization. Mike has been a moderator in the past, as well as a presenter, and I'd like to turn over the presentation now to Ewan.
Mike is the Global Director of Iron and Steel Technology for Air Liquide. He's had many years of experience in the industrial gas industry. With Air Liquide, he's presented more than 60 presentations on iron and steel technology and holds 8 patents. Mike, is there anything that I overlooked?
No, that sounds very good. Thank you very much. That more than does the trick. Thank you, Ewan. I would like to say a few words about the Decarbonization Subcommittee for the AIST. As we all know, decarbonization has been a topic highlighted by many countries, driven often by legislation. The Decarbonization Group has the responsibility to collect, communicate information to the iron and steel industry as it relates to the topics of decarbonization. Individual technology committees in the AIST and the member chapters have regularly been holding functions to educate the iron and steel industry on the topic of decarbonization or CO2-free steelmaking. And this has been going on for at least the past 2 years. In 2021, the AIST decided to create a subcommittee called the Decarbonization Subcommittee. We are a subcommittee of the Energy and Utilities Committee. And from our activities up till now, the AIST members have demonstrated a strong eagerness to learn learn about decarbonization. So we created a mission of decarbonization subcommittees to gather, collate, and disseminate information that brings together experts from across the industry to educate and aid the journey towards sustainable steelmaking being the core of a sustainable global economy with short, medium, and long-term goals, and pathways addressing industrial transformation and education of young professionals. And with that, I will hand it back to you, Ewan, to make the first, to introduce the first speaker.
Okay, that's great, Mike. And I thought I should also mention that, this particular session was prepared in response to steel industry interest in understanding the experiences and challenges associated with the combustion of low carbon fuels. The presenters will cover practical and theoretical aspects of combustion of hydrogen and ammonia from the perspective of a steel producer, an industry supplier, and also a governmental research group. And with that, I'm pleased to introduce our first speaker, my friend and colleague, David Muren from Linde. David is the Director of R&D for Metals and Combustion EMEA. He's had more than 25 years of industrial gas experience with Linde in various roles in operational and management positions, as focused on the development and commercialization of industrial gas technology. He's an expert in Oxy-Fuel combustion, and in recent times he's been focusing on the utilization of hydrogen as a fuel. He holds 2 patents related to combustion and industrial gas, and he has a master's in metallurgy from the Royal Institute of Technology in Stockholm. Now with that, David, you can take it away.
Here we go.
Now it looks good, and I'm going to drop off.
Thank you. So first of all, I would like to thank the organizers for providing me this opportunity to share the work that my team has done over the last couple of years. So as the title indicates, we'll be talking about development. First of all, a little bit about how the team is spread over the world in our areas of focus, and then something of I tried to pick some of the specifics on hydrogen, specifically as it pertains to fuel, and then of course how it's combined with our existing work in Oxy-Fuel, and specifically flameless Oxy-Fuel over the last 20 years, and also how we have developed and tested this technology together with some of our end user partners over the last 5 years or so. So looking at Linde technology, first of all, I should say, as was mentioned in the introduction, Linde as an industrial gas company, of course, has many, let's say, areas, irons in the fire when it comes to decarbonization, carbon capture, hydrogen production, and supply of other industrial gases that will be required for this decarbonization journey. What my focus is, my personal focus and my team's is the use of these industrial gases in the process. So for this presentation, it will be mostly around Oxy-Fuel and hydrogen Oxy-Fuel. I'll try to answer any other questions, but they're really more peripheral and something I've picked up over the last 30 years or so. So my area of responsibility is the EMEA part, and specifically in Central and Northern Europe, where of course EU's Green Deal has meant a very strong focus on decarbonization in the last 5 years to meet the ambitious targets of 50% reduction by 2030 and then climate neutrality by 2050. How viable that is and how many the obstacles are, I don't think I need to mention, but it clarifies that the use of hydrogen is not only trying to find a, let's say, a commercially or a cost competitive way forward, but it's actually a must. So we that hence the push for hydrogen applications, and also hydrogen because it has been deemed as one of the most viable ways forward to quickly decarbonize the steel industry by the European Commission. So looking out at the global view of how Linde is supplying industrial gases, we're divided into three operating segments: the Americas, EMEA, and APAC. That doesn't mean we, or I should say, we do cooperate over the borders very intimately, and technology travels in between. But each hub has a let's say a focus on their areas. So quite naturally for EMEA, that is decarbonization and then hydrogen combustion. So if we look at why we would, why specifically this is an area of interest, especially the flameless approach. In Scandinavia and Europe, especially reheating technology has been an area of focus over the last 30 years or so, where we have, especially with the flameless combustion, as I mentioned, in the last 20 years have had a lot of success and very good process performance, as you can see there, especially on the last 3 points: reduction of NOx and improved temperature uniformity, and even decreased scale losses in some cases. But the driving forces throughout this journey has, up till very recently, I should say, always been capacity increase in almost all cases. Then things like NOx emission and temperature uniformity has been a qualifier to be able to implement and this technology. Now fuel savings has been up to recently more of a, let's call it the hygiene factor. The fuel savings in most cases need to at least cover the cost for oxygen, and in Europe and especially in Scandinavia, that has in most cases been viable, since fuel prices are high, and also with added fuel taxes since many years. Now the decarbonization, of course, has put a different focus. Now the subsequent CO2 emissions reduction that comes with the fuel savings has been a focus, and that's of course in parallel with the fuel savings if you don't do fuel conversion, where it can get up to 100% if you're using green electricity to produce the hydrogen. Now, looking at hydrogen as a fuel compared to, say, natural gas or methane, which most of us are used to, I should start by saying that hydrogen as a fuel isn't, of course, not new as such. It's the major component of coke oven gas. So its properties should be recognized or known to large parts of the steel community. Of course, the significant part of hydrocarbons and some CO in the mix makes it quite a different fuel to the purity of pure or the cleanliness of pure hydrogen. Now, I brought up a couple of related properties of hydrogen and methane, just to give some indication, and I think perhaps many of these are known to the audience, but just to point out the significance. So it's often brought out, the first three points here, that the increased flammability over the broad range of concentration, the flame speed and and also I should say the lower ignition energy required to ignite hydrogen as a danger in hydrogen as a fuel. Well, I would say actually if you're trying to do combustion, it's not a bad thing. We've seen over the last 5 years that using hydrogen as a fuel is extremely undramatic. It ignites very quickly and without any bangs, and it keeps the flame stable. It provides a UV signal. So as you do combustion, or when it comes to igniting and operating a burner, hydrogen is a great fuel. Well, the drawback can be things like, let's say, challenges in design, both burner design and process design can come in operations where you risk having communicating vessels, so that the oxidizing media, whether it's air or oxygen, comes into contact with the hydrogen and mixes in places where you don't want it, the piping or somewhere going back. So any type of pre-mixed combustion or high pressure combustion, you need to be beware of flashbacks and make sure you have very tight operation procedures when it comes to purging before ignition and after the burner is turned off. Then moving to the right, the energy content of lower heating value is about 30% in hydrogen compared to natural gas. So you need obviously then 3.3 times as much hydrogen as natural gas to do combustion. But then the required oxygen, whether it's air or pure oxygen again, will be only a quarter. So that means that the off gas amounts per energy unit is going to be similar, which is good news for things like dampers and the flue gas systems and overall furnace structure if you're converting your process. Now, another thing, although as I said, the volume flow is 3 times higher, the density of hydrogen is low, and hence the pressure drops. So it's rarely required to make significant increases in size in your combustion system, especially if you have the higher supply pressure that is at least often, most times, optional with a hydrogen system. Another thing, another consequence is that any leaks will disperse upwards rather than stay in the area or drop low, which is going to be an important aspect when you look at your ventilation and where a potentially hazardous leak, where that would end up. When it comes to leaks, we should, of course, also point out perhaps an obvious fact that the small hydrogen molecule will be easier to leak out of any untight part of your supply system. In reality, we have not seen that this is a major issue if you do the work right and try to have good quality flanges or similar connections, and try to keep the number down and use reasonably good materials, not very extreme, but just good type materials. That is usually not an issue in our experience. I should say also that hydrogen is clean and easy to work with. You don't have any grease coming out of it, any condensation, any soot. It's non-toxic, so quite a convenient fuel to work with. Actually better than most, I would say. One thing is that the flame temperature with hydrogen is higher than with the methane. So that can present a potential problem with NOx formation, as it's dependent on peak flame temperature in most industrial processes. I will comment on that a little bit later in this presentation. Now, when it comes to Oxy-Fuel properties, why Oxy-Fuel? Well, the flue gas volumes are lower and hence the flue gas losses. If you look at these two comparisons with the reactions described below, you'll see that the nitrogen from the left side, the reactant side, carries through to the product side unchanged, basically, which means that 8 of the 11 molecules on the reactant side, 73% is going to be nitrogen. Now, all that hot nitrogen is going to leave the process as losses unless they are captured through some type of recuperation or regeneration system, which would represent these two lines. Now, a typical heating process at around 1200 C, which is 2200 F, I think, would be at slightly above 80% if the flue gases leave the process at this temperature, which would be some type of batch heating. Correspondingly, even if you have a good preheating system of, let's say, 300 C, I won't chance on that in F around 500, I guess, 550. The efficiency would drop down to, say, around 55%. Now, if you have a dark zone in your furnace, your off gases wouldn't leave at the high process temperature. They would drop down to around, say, 900 degrees. So the numbers would look slightly better, but still it's a significant change between the 70% for preheated air fuel and the around 85% for Oxy-Fuel technology. So flue gas losses is one important part, and the amounts that are lower. The other part is the composition of the off gases. Now, at higher temperatures above 1800 F, the dominant heat transfer mechanism is going to be radiation, and two atomic gases radiate to a much lower degree than the three atomic ones, as they move in their bonds. So with the Oxy-Fuel combustion having a more strongly radiating, stronger gas radiation component than the air fuel, you will have a stronger and more uniform heat transfer if you move that hot gas around in your process. Now, these two in combination lead to a lower mass flow of off gases, means a longer residence time, and improved heat transfer means that the temperature will come closer to equilibrium. So you'll have lower off-gas temperature further in Oxy-Fuel than you'd have in air combustion. Now, you can also use that to fire harder as you don't, as the off-gas amounts are lower. Both these will lead to energy savings and CO2 emissions.
So David, I've just popped up to give you a 5-minute warning here.
Okay, very good. I'll speed up.
Okay.
All right, so the way we see it, that hydrogen will be an expensive fuel with limited availability. Of course, we hope that this will improve, and I'm sure it will over the next couple of years, but still it will be more expensive than most other fuels. So using Oxy-Fuel with improved combustion efficiency will make sense, and it will also provide a decarbonization effect. Now, showing this in a different way in this diagram, from a starting point here, and looking at CO2 reduction on the x-axis and fuel savings on the y-axis, you could move directly towards air hydrogen combustion and achieve the CO2 reduction, provided that you use green hydrogen. But taking the route via Oxy-Fuel first to create the fuel savings and the starting CO2 savings, and then moving to full hydrogen Oxy-Fuel will mean that you have a more efficient use of your expensive fuel, and you will also prepare your process, because these two processes will be a lot the same, lower off-gas amounts than compared to these processes down here. So this would be the route we would recommend to go to reach decarbonization using hydrogen as fuel. Now, another important factor is the flameless combustion that we developed in the beginning of 2000s. Now, separating fuels and oxidants fully, looking at this picture where the oxygen comes out concentrically around the fuel, and in the second where they're separated, where you have fuel up here and oxygen here and a very vague bluish flame over here, we have a lot of recirculation and an extended and increased combustion zone. That means low flame temperature even with hydrogen as fuel. Now, this was tested at our combustion lab in Stockholm in 2019 with the material from our customers, using both engineering steels and stainless steels, and doing a heat up and a 1, 2, and 3 hour soaking of the material to look at both the combustion properties but also material properties like scale formation, decarbonization, or decarbonization, I should say, of the steel, and any effect on the alloy. What was concluded in these tests were that there was very insignificant effect on scale formation and any type of the base material. Also, we saw that we could achieve similar concentration emissions of NOx as with natural gas as fuel. Now, we did similar trials with aluminum melting. Here, the focus was to look at dross formation and also the content of hydrogen in the melt. These were quite successful, and we showed that even high magnesium-containing alloys that are sensitive could be processed without any concerns. Now, getting to the summary then. So Oxy-Fuel combustion with existing fuels will significantly reduce CO2 emissions by increasing fuel efficiency. We have demonstrated that reheating first furnaces and aluminum melting can be operated with hydrogen as fuel without any negative impact on the process or the materials heated or melted. Flameless Oxy-Fuel works well with hydrogen as a fuel and maintaining the benefits of low NOx formation and temperature uniformity in the process, I should say also. So we see that use of energy Oxy-Fuel combustion decreases the required volume supply of hydrogen for the process. Now, 3 of our 4 Linde technology centers globally are equipped for hydrogen combustion, and the 4th in China is looking to do that in the next year or so. That's the end of my presentation. Thank you for the time, and I'm sorry if I ran a bit late here.
You're pretty close, David. You're only 1 minute over, so I think we're pretty good on that one.
Thanks, Joan.
So in response to one of the questions in the chat, there was a question, David, on availability of slides after the presentation. So people that are interested in that can reach out to David directly. I see that we've got his email up on screen now. And then looking through the other questions that are in the chat. One of the points that's been raised, and it often is when people are considering hydrogen combustion, is that since the density of hydrogen is much less than other gases, does that affect the size of the nozzles? And for that matter, does it affect the size of piping as well, right? Will the hydrogen nozzle be larger or smaller than a regular lance? So maybe, David, you can comment on the experience, converting fossil fuel fired systems to hydrogen, the changes required, and how difficult it is to do.
So it's a very good point, and you can say that there are two mechanisms that I mentioned. First of all, the lower energy density means that you need to put through 3 times of the flow, but then the lower density also means that there's lower flow resistance to the hydrogen going through. What we've seen that you need to have a slightly higher pressure to use basically the same equipment as you have today. Somewhere it's going to be dependent, but somewhere between 20 to 30% higher than what you have today. So it is slightly higher, but not dramatic or significant in most combustion systems. Especially, as I said, since the hydrogen most of the time will come supplied at a higher pressure than the natural gas, and then provided that your combustion system can tolerate that. Now, when it comes to nozzles, yes, higher flow through, but then you also have the aspect of increased flammability, and also lower mass of the gas stream coming out. So these two effects seem to, at least in most of our, let's say, stage type combustion, counteract each other, so you can achieve the same type of flameless combustion with a higher flammability, let's say. So higher speed of the gas and increased flammability would counteract each other, so you'll still achieve similar type of performance, I would say.
Okay, thanks. There's a question with respect to the economics of Oxy-Fuel. So not specific to hydrogen, but Oxy-Fuel in general, relative to air fuel. I know that you have a lot of experience looking at that in different parts of the world. Can you make some general comments on that?
Yeah, I mean, the general comment would be if your fuel is cheap, it's going to be much more challenging to motivate you using oxygen as an oxidant compared to air. Now, with that said, if you have on-site production, you might have periods where you have excess oxygen available, and we have systems and methods of hybrid oxygen combustion where that oxygen can be utilized when it's available, and then you can revert to your air combustion when it's not. Another interesting aspect is if you have on-site hydrogen production, you will also produce oxygen. Now, how that is captured in your electrolysis is a different story, but going forward and when the volumes get greater, if that oxygen is captured, dried, and pressurized, it can be used in the combustion process. I think our next presenter may comment on this, actually.
Okay, and there's one final question which I think is relevant with respect to safety. A couple of attendees have asked about flame monitoring with hydrogen. Can you quickly comment on that? Because I think we're at the end of our Q&A session. We want to move on to the next presentation.
Sure. No, yes, that's a very good point. So hydrogen combustion will produce UV, actually very strong UV. So UV sensors can be used without any problem. Actually, probably work better than what they do with natural gas. You will not be able to monitor your flame through ionization. So that's a limiting. UV, yes. Ionization, no. That's my summary.
Okay, very good. So Mike, I'll turn it over to you to introduce the next presentation. Thank you very much, David, for the information you provided.
Thank you, David. Thank you, Ewan. It's my pleasure to introduce Anders Lugnet, Group Technical Specialist responsible for energy and furnace technology at Ovako. He has more than 29 years of experience of industrial heating process optimization with a specialization on steel reheating furnaces. He does this from the perspective of mechanical design, project management, research and development to determine the best use of best practices. And he is the project manager in a furnace engineering company to process development in steel reheating and burner and combustion process research and development. Since 2012, he has been responsible for energy furnace technology and has a coordination role in implementing the world's first industrial scale hydrogen Oxy-Fuel steel reheating furnace. And with that, please pay attention to Anders Lugnet of Ovako Group. Thank you very much.
Excellent. Okay, thanks for the introduction. Happy to be here today and talk about our really interesting project within Ovako. I will not talk anything about the company Ovako. If you're interested in what we do, please go into our website and have a look. So, decarbonization has been our mission for a while. In Sweden, we have a lot of fossil-free electricity. So it is pretty simple for us to decarbonize if we just make use of the electricity. If we divide our steel plant into three parts, we can say that we have the melting part, the heating prior to hot forming part, and the heat treatment part. And traditionally, all these have been very fossil heavy. When it comes to the upper part here, the melting part, Ovako have been using electric arc furnaces since 1930. We shut down our last blast furnace 1978. So since then we have really electrified the melting part. When it comes to heat treatment, in the past we used propane or coke oven gas when we had blast furnaces, but now we have really electrified everything, directly electrified. So we don't use any natural gas or propane in this process any longer. The difficult part has been heating prior to rolling and forging, and that's what we are doing now with the use of hydrogen and oxygen from electrolyzers. So we use fossil-free electricity to split water into hydrogen and oxygen. So we in Ovako already have a uniquely low carbon footprint. It's the lowest in the industry. And this is the split we have where our CO2 emission come from. About 64% of our carbon dioxide emissions comes from combustion. And all that part can be replaced by hydrogen. And we have a plan to up to 2030, all our combustion carbon dioxide will be eliminated, and we will use hydrogen from electrolysis to do that. Next stop will be biochar instead of petroleum coke and anthracite, but that's a different story. So the French science fiction writer, author Jules Verne said this 150 years ago: "The energy of tomorrow is water that has been decomposed by electricity." 1875, that's pretty amazing. 1875, most people didn't know about electricity at all, but this guy talked about what we are actually doing now, 150 years later. So why do we go for hydrogen as fuel for reheating furnaces? David has explained most of it, but if we look at it this way, rolling mills normally use fossil fuels such as natural gas, propane, or oil to fire the furnaces, and most often with air as oxidizer. And this usually gives a carbon dioxide load between 100 and 200 kilograms per ton of steel in the rolling operation alone. And these processes are extremely difficult to electrify directly with resistive heating. So hydrogen as fuel with pure oxygen as oxidizer, that will give the highest efficiency and zero carbon dioxide emissions in the reheating process if the electricity comes from fossil-free sources. Other things that's a really good advantage in reheating is that when you use hydrogen, there is absolutely no risk of carbon monoxide at all. So it's a good environmental thing within the factory and for the people around the furnaces. Also, when we use electricity and water to do this, we do get less dependent on fossil fuels from other countries like Saudi Arabia and Russia. We can use our own hydropower and nuclear power and so on to do this. So these things are important factors. First of all, of course, decarbonization, but also carbon monoxide and also the energy dependency. Our systems, there were questions about changing nozzles and stuff. We use Linde burners, flameless, made for propane, and it is absolutely no problem at all to use those burners with hydrogen instead. And we can switch fuels in a split second, and that's what we do. And because of this, we actually don't need hydrogen storage. We're not dependent on hydrogen. Our storage is our propane tanks. We have 800 tons of propane as our energy storage. So we only have a very small hydrogen buffer, really, for half an hour's use or something like that. And so we don't we use the hydrogen in the same pace as we produce. So I would say about 15 years ago, the thoughts came into my mind about using hydrogen and oxygen. And the reason for that was that the environment around these furnaces were really terrible. They were, at that time, many of them were heavy oil fired furnaces, and it was smoke, soot, and carbon dioxide, and oil leakages and stuff. So and at that time I thought that, okay, hydrogen and oxygen, that must be the future when it comes to clean factories and so on. And in 2020, in March, it was really COVID had shut down the world, but Ovako, together with Linde, we made the first full-scale trial during this period, and we showed that this works also in real production. Lab is one thing, but how will temperature uniformity and so on be? And but we did this in production scale, and we showed that it worked. And this was extremely important to show. I mean, it would have been a showstopper if the results were not as good as when we used LPG as fuel. But the trials, they showed that it was no negative impact whatsoever on product quality or rolling results. And so from this point on, we really well tried to work to implement this in a larger scale. And how did we get there? We had a strategy that was really our board took it some 10 years ago, 11 years ago. And at that time, the strategy was to how could we reduce fuel use and so on, but it was really adjusted 2020 to how can we reach zero emissions. And the points have been that we will use electricity wherever possible, and we will use direct electrification where possible. And we think, okay, below 1000 degrees C, it is you can still have good productivity and so on with direct electricity. Another point was that we will go away from oil and we will go towards LPG. We will change our air fuel systems to Oxy-Fuel systems, and we have done that. We have 60 installations today with Oxy-Fuel. And also we standardized how we work with our control and automation equipment. We have in the company about 130 furnaces, and it's important that we don't have too many different systems here. What we added 2020 after our full-scale trials was that when possible, we will use hydrogen from electrolysis of water instead of LPG. So and that's, as I said, that's what we have been working with. And today we have built a electrolyzer in this part of our mill. This is the Hofors site, and so here's the steel mill, and here's the rolling mill, and we have a forge shop over here. We have a ring forging mill and a tube mill here. And this building was an old tube mill that hasn't been in operation for a while, so we really had the building to use. So today there is a electrolyzer, a hydrogen plant here, and we have new infrastructure for hydrogen, because we didn't have any hydrogen before, but we had a big infrastructure system for oxygen. So the oxygen from the electrolyzer is actually taken into the existing system. There are on paper advantages to use old building, but it's I would say not recommended to do that, because it's a lot of things that you don't plan that happens. There are, yeah, quickly I can go through here the different parts where we put things. So in the basement we put the water purifier, we put transformers, 2 of them, 4 rectifiers. On this left side we have the 2 hydrogen compressors, buffer tank, gas holder, scrubber, and so on. And on this other side we have the right side we have the light tank, we have a gas holder, compressor for oxygen, and scrubber. And on the first floor we have the electrolyzer house. It would have been much easier to make a new building somewhere else rather than using this old building, for sure. It took longer time and it was more expensive than expected. But this is what it looks like today. And professionally, this is a real milestone for me. It's, I mean, to use fossil-free electricity to split water into hydrogen and oxygen to replace fossil fuels. This makes a difference when it comes to decarbonization. And this is, as you see, the real thing. It's of course it's a PowerPoint, but this is as close as you get without actually being there. And for Ovako, this is really the starting point. We will make 5 or 6 of this type of hydrogen plants until 2030. That's our plan. So we are trying to take the lead in this area, and I think the picture says it all. I mean, our industry doesn't need to be dirty. This is really a clean energy in a clean environment. So what about the energy balance? Is it worth it? Well, you often hear that it takes huge amounts of energy to produce hydrogen, and the efficiency is terribly low. But I think in Ovako's case, that's not correct. If the target is to eliminate carbon dioxide from the process, I would say that this is by far the most efficient solution available. And Ovako's concept, we don't only use the hydrogen, we also use the oxygen, and we do recover some of the waste heat from to our district heating system. So the efficiency is about 76% at full load, and I would say that's not bad at all. And that's before any flue gas recovery. So what you see here is that the green colors show useful energy, the red is losses, and blue, that's the potential for flue gas recovery. So what do we think is the success factors to do this? we for sure believe that you need a large continuous hydrogen offtake at low pressure, and when I say low pressure, in our case it's up to 39 bars, but with today's standard, that's low. You often hear gas industry talking about 700, 800, 900 bars now on hydrogen, but of course it costs to compress. So I think a large continuous offtake at low pressure. Also, we believe that you should build systems where you don't need to have huge hydrogen storages, because hydrogen storage is extremely expensive. It's we would rather buy another electrolyzer than making a storage. We have our existing LPG infrastructure as storage. Also, it doesn't make you dependent on hydrogen. So as I said earlier, we only have a very small hydrogen buffer. A prerequisite for sure, I would say, is that you have efficient Oxy-Fuel technology in place. Both it lowers the energy usage, as David said in the presentation prior to this one, and also you make use of the oxygen produced when electrolyzing. And another success factor here is that we have a lot of in-house competence in an innovative environment here, because you cannot buy this system off the shelf. We have done a lot of engineering ourselves. So these were the success factors. And by that, I'm ready.
Well, thank you very much, Anders, for an excellent presentation. Very interesting, and it shows that definitely Ovako is working in the future. I have several people are very interested in your presentation, so there's several questions to be answered. So I'll start with the first one. Your EAF doesn't have any natural gas burners, is that correct? Or do you have supersonic oxygen in your EAF?
We have 3 EAFs, and 2 of them use supersonic burners. Yeah, with propane today, but we will for sure try hydrogen on these ones.
Okay.
But that's not the first step.
Okay, thank you. Are there any efficiencies or reduction in power demand to be realized when utilizing hydrogen as a fuel source in designing the overall system to produce metals?
Well, in our reheating furnaces, we already have Oxy-Fuel systems installed, and to change from, in our case, LPG or natural gas to hydrogen is really no issue.
Okay. What about induction heating? Is that in place of oxy-hydrogen? Was that considered as an alternative?
Yeah, we have a number of induction furnaces. It's you can heat billets or bars with that. You cannot heat ingots, and especially if you have long soaking times from between 5 and 20 hours or so, it's not a viable option.
Okay. And do you have any comments on the purity of the water for electrolysis? Is that something
Absolutely.
you?
Yeah, we start off with drinking water, but our drinking water is not clean enough. So we have water purification in 3 steps, reverse osmosis, and I'm not an expert in that, but the cleaner the better, for sure. Yeah.
Okay, but distilled water is not used, is it, or is it?
Well, we start off with drinking water, but basically it is better than distilled when we introduce it to the electrolyzer.
Okay. And
the important part is to take away the minerals and salts, because they will destroy your electrodes over time in the electrolyzer.
okay. And how long did it take for the investment to pay off for this, or has it happened yet?
Extremely difficult question to answer in a few minutes. It will probably take an hour or two, but I would say that if you have customers that will pay just a little bit extra, it pays off. Also, it's very much depending on the electricity prices, of course. Right now, the electricity price is very favorable in Sweden compared to propane, so it is cheaper to run with hydrogen than propane right now. But it's very, of course, it's in a volatile world. We don't know. We will see when it pays off. But we think it's a good investment. And we will do more of those.
So thank you very much. That's all the time we have. So I'm going to pass the seminar off to Ewan to introduce our last speaker. Yeah. And I really appreciate Anders for an excellent presentation. Thank you.
So thanks very much, Mike. And I'm pleased to present our final speaker, who's Dr. Clint Beddick. He's a research engineer at the U.S. Department of Energy, National Energy Technology Lab in Pittsburgh, PA. He works in the Energy Conversion Engineering Directorate within the R&D Center. He earned his PhD from West Virginia University in 2009, and he's worked at NETL ever since. And his research is focused on oxy-fuel combustion, turbulent flames, direct power extraction, and pressure gain combustion. He's also interested in advanced diagnostics. Currently, he's leading an effort at NETL to investigate the use of ammonia as a carbon-free fuel in gas turbine engines and industrial heating applications, and that's going to be the focus of his presentation today. So Clint, if you want to screen share. Looks good.
All right, is everyone able to see the right screen?
Yes.
All right. Yeah, thanks for the introduction, Ewan. So what I'm going to talk today a little bit about is, looking at ammonia as a hydrogen carrier, specifically the combustion considerations. Sorry, 1 second. Doesn't seem, there we go. So just quick disclaimer, federal government disclaimer. And so I'm just going to give a quick picture of what the National Energy Technology Lab is. So we're one of 17 DOE national labs in the US, really focusing on looking at energy research and development. We're one of 3 applied research labs, and we're uniquely government owned and operated. So we have 3 locations, Albany, Oregon, Pittsburgh, Pennsylvania, where I'm located, and Morgantown, West Virginia. And there's kind of 2 arms, one which is they kind of look at administering and monitoring the DOE funded projects that go out for solicitation and award. And then the other is the in-house research that goes on at these labs. And so that's where I work. Some of the major initiatives, looking at now is decarbonization, carbon management, and that's kind of where this ammonia work falls. Also do a quick plug for, so NETL started a technical working group on ammonia combustion. So if any of this stuff is of interest to folks, I encourage you to send me an email at the end. We have kind of distribution list, and we get together every other month. It's kind of just an informal meeting for, information sharing and general discussion of ammonia. We have a couple of presenters each meeting. and then time for open discussion. And also, you can get on the NETO website and see kind of proceedings and presentations from past meetings. So what I'm going to talk about today, sort of, why ammonia, starting there, some real brief comments on kind of the production and transport and storage aspects. And then most of what I'm going to look at and focus on here is the bottom portion. So really the fundamentals and unique technical challenges of ammonia, looking at things like model validation, doing this in more applied systems, introducing the concept of air staging for ammonia, and then closing it out with some look at oxy-ammonia combustion. So, really, what's the role of ammonia? Certainly a hydrogen carrier, right? So there's 3 molecules of hydrogen, 1 nitrogen molecule. Similar to hydrogen, it can be a carbon-free fuel, and similarly, it can be used as something like chemical energy storage in the energy sector. It addresses a few of the challenges with hydrogen, and so that's really the main interest here is hydrogen has this low volumetric density, so you really have to store it at high pressure or very low temperature to get it into a liquid. And all that can be energy intensive and have high capital and operating costs. And on the contrary, liquid ammonia, you can store it at about 10 bar or minus 33 C. So it's kind of more in line with what we're used to with like LNG and LPG fuels. The other big advantage here is an existing ammonia industry, mainly surrounding agricultural applications. So it's everything from synthesis, transport, and storage. And so one application or one use here could be using ammonia, converting to hydrogen to ammonia, transporting it, and then converting it back before utilization. But really a big interest would be in direct utilization. So if you can avoid that reconversion, directly use it in gas turbines or furnaces, there's certainly going to be an efficiency advantage there. So ammonia production usually is done using the Haber-Bosch synthesis. So you have to generate hydrogen. You combine hydrogen and nitrogen at high pressure over a catalyst, and you generate your ammonia. Similar to hydrogen, there can be various colors depending on the carbon intensity. Ultimately, we would hope that we're going to get to this fully green scenario where we're electrolyzing water. The last presenter showed some really great examples of that. And then obviously going to ammonia is a second step where you're going to need additional sustainable electricity input. Kind of in the interim, and what's typically done now is utilizing fossil fuel feedstocks, doing some reforming to get hydrogen and carbon dioxide. We can have a blue route if we can capture that. Otherwise, it's going to be considered sort of a gray or brown, which is going to have potentially a considerable CO2 impact. There are existing worldwide shipping routes and pipelines in the US for ammonia, so that infrastructure does exist and could be expanded. And then one of the other considerations here certainly is ammonia versus hydrogen. And really comparing these things, this is some results from an IEA study that was done a few years back, looking at costs of transport. And really one of their findings was that hydrogen made sense for shorter distances, but as you got to longer distances or long shipping routes, it made sense to convert to ammonia to do that transport and then convert back on the other end. So I'm going to talk about the fundamentals a little bit, but first I just want to point out that while it's kind of new to look at ammonia as a carbon-free fuel, it has been done in the past. Back as far as the 1940s, there were recip engines running on mixtures of coal gas and ammonia. In the 1960s, the NASA X-15 used ammonia as a fuel. Pratt Solar Turbines looked at it as a fuel. And their general findings were, it was tough to burn. The scale was important, how you design and modify a combustor. In a lot of cases back then, they had to use additional catalysts and different things to kind of improve the combustion characteristics and get these things to run. From a fundamental property perspective, so certainly ammonia has a lower heating value and flame speed compared to hydrogen or our hydrocarbon fuels. There's also some volumetric energy differences. So it's about 40% that of methane. So you're going to end up needing about 2.5 times the fuel flow for equal power output, and certainly a narrower flammability range. The low flame speed of ammonia makes blending with another fuel seem favorable. So these are just some plots on the left that we generated using some simple 1D modeling, where the bottom's equivalence ratio. So it's maybe contrary to I know the industry likes excess air. So above 1, rich; below 1 is lean conditions. And so just highlighting that the orange line here is 100% ammonia air. The blue line here is methane. So you can kind of blend your ammonia with varying amounts of hydrogen, and you can kind of get it, at about 50%. You can sort of match that methane flame speed. Methane is another thing you can blend with. Of course, there's still going to be carbon emissions in that case, but you're going to need a lot higher blending ratios to kind of get the flame speeds up to be comparable with those methane systems. Just some photos. These are photos we took at NETL as part of some of our flat flame experiments that we have going on, just to kind of give an idea what these flames actually look like. So we have hydrogen flat flames on the top, methane flat flames on the bottom, blended with different amounts of ammonia by volume in the fuel. And so on the left, with low blending amounts, you get very nice, well-behaved flat flames, nice thin reaction zone. It's very well stabilized. And as you add that ammonia, certainly you start seeing this characteristic orange color, which is from the emission from ammonia-based compounds. And then you also see the flame zones thickening considerably. The flame starts to stand off and start to wrinkle up, and eventually it's going to end up blowing off. That blow-off point tends to be sooner for the methane, just because it has a lower flame speed compared to hydrogen. One other effective way to enhance the flame speed and combustion properties here is using cracking. So you can thermally decompose ammonia to hydrogen. You're going to have some blend then of ammonia, hydrogen, and nitrogen. You can do this in the absence of a catalyst, but it's been shown that some simple, widely available ruthenium-based catalysts can be pretty effective. And so depending on temperatures and kind of residence times in these reactors, you can almost fully decompose your ammonia to hydrogen with that process. And then the final one is you can obviously enhance oxygen concentration, and that's certainly going to increase your flame speed, increase flammability. It is likely to impact emissions. So this is just a plot from the literature, just showing, down here on the bottom, the ammonia air. These other gray dots here are methane air. And so if you increase the oxygen content from 21% in air to 35%, you can really more or less get your flame speed to kind of match that ammonia case, or the methane case. And so kind of the crux and the big challenge here in ammonia is NOx formation. So this is pretty challenging to overcome, and it's really because of this fuel-bound nitrogen. So it's a very different mechanism than what we're typically used to in hydrogen or in methane. And so it can result in very high NO concentrations. And so these are, again, some modeling results we did, where we kind of show down bottom here is the methane air case. You might expect 200 parts per million NOx at stoichiometric conditions. Under lean conditions with ammonia, you can be as high as in the thousands of ppm. Blending with hydrogen tends to exacerbate that, especially at these lean equivalence ratios, where you can get up to very, very high NO concentrations. If you look on the rich side, you certainly can mitigate a lot of that NOx formation, but then you start getting lots of unburnt ammonia coming out in the flue gas. And this is really driven by the reaction pathways that are very different for ammonia than hydrocarbons and hydrogen. So it originates from the fuel rather than nitrogen dissociation. That high temperature thermal NOx route does still exist, but it tends to be overshadowed. And these fuel pathways greatly depend on kind of the radical pool here. So O, H, OH, these kind of combustion intermediates. So operating at rich conditions can limit a lot of those species and limit the NOx formation. The other unique thing with ammonia is that elevated pressures tend to reduce the NOx concentration, which tends to be contrary to what we're used to with hydrocarbons. So I'm going to go through this one pretty quickly, but just to say that, I showed results from modeling results over the past few slides. There's lots of available kinetic mechanisms specific to ammonia. Some have carbon, some don't. There's a major need still for validating all of these models. So these top two plots are just some validation that we've done at NETL, measuring laminar flame speeds, comparing to some kinetic models for different ammonia mixes. And down in the bottom right-hand corner is some basic species measurements done from the literature. And you know, kind of as you can see, the amount of agreement tends to vary pretty considerably. So I think we still need a lot of validation of these models. So in terms of applied combustor, so just looking at something that looks a little bit more like what we'd expect in a a gas turbine engine, for example, or a furnace. The stabilization mechanisms we typically use are still effective for ammonia air. So this is kind of a swirl combustor. It's strongly dependent on recirculation zones. So that low flame speed tends to want a lot of kind of hot products to be promoted into the mixing and reaction zones to help stabilize and anchor that flame. So down here, you can see just an example of what some of these flames look like. And one thing to point out here, if you compare the kind of the methane air case, you have this nice compact flame. When you go to some of these ammonia flames, they tend to fill out the combustor pretty considerably. And that's really just, again, driven by the slow kinetics, the low flame speeds of ammonia. Along with this study, they measured emissions. These are experimental emissions from this group that was in the literature. And so you can kind of see that they more or less have the same trends that we saw in the prior slides for the model results. So, NO emissions under lean conditions in the thousands of parts per million. As you go to these rich conditions, a lot of unburned ammonia. You also tend to convert some of that ammonia to hydrogen, which we'll talk about kind of what we can do with that in the next few slides. And so that brings us to this concept of air staging for ammonia and the two-stage combustor concept. So we can kind of demonstrate this concept with a model we developed at NETL, which is a chemical reactor network model. So we have two of these perfectly stirred and plug flow reactor arrangements. And so this is kind of meant to mimic sort of a flame and a post-flame zone. And so you have one rich reactor, you have secondary air injection, and then you have this lean reactor. And so this gives us this so-called rich quench lean arrangement. And the rich stage, really the idea here is to run at rich equivalence ratios, so you don't generate a lot of NOx, and you want to maximize the ammonia to hydrogen conversion process. And so this is just a plot showing the model results from that rich stage. And so you can see if you operate at these rich conditions, you're generating a good amount of hydrogen here, which is shown by these solid lines. And then you're kind of trying to get into this sweet spot of not having too much unburned ammonia. So in the second stage, you're going to kind of burn that hydrogen. The remaining ammonia is going to get burnt out, and you're trying to minimize that fuel-bound NOx. And so if you look at kind of the output of that whole model out of the lean stage, and we look at that as a function of the rich equivalence ratio, rich stage equivalence ratio, and then these different lines are varying amounts of secondary air injection. And so really the takeaway here is it's very sensitive to this rich stage equivalence ratio. And if you really kind of get that right, you can have a dramatic effect on the NOx emissions. And so you can see kind of in the middle, if in this instance, if your equivalence ratio about 1.3, you're able to get sub 100 ppm NOx. Certainly these are just modeling results, so take those numbers with a grain of salt, but it's encouraging in terms of using this approach. There's some instances of experimental demonstration here. This is some results in the literature from an atmospheric example of this, where they kind of had a pre-mixed bluff body stabilized burner, and then they added the secondary air injection ring kind of further downstream. And so this is just some imaging they did where you can kind of see this first stage flame down in here, and then up in the secondary air injection ring, you get this second luminous zone where it's that lean stage burnout. And they measured the species out of here, and more or less the trends confirm kind of what we saw on the prior slide there, where there's some pretty good sensitivity to that main stage equivalence ratio, and you can get reasonably low emissions in the middle of that, in like just above stoichiometric conditions. Certainly the NO that they measured here was not as low as what I showed from the model on the prior slide, but I believe this is a fairly unoptimized system still. The other thing I want to do is just highlight some recent progress by Creative Power Systems and University of California, Irvine, and they presented these results at our July Ammonia Combustion Technology Group meeting. And so I just took two of their slides just to kind of show, again, the promise of this two-stage RQL arrangement for ammonia. And so on the left was atmospheric pressure results, where they looked at, again, this is the rich stage equivalence ratio, and this is their corrected NOx numbers. And you know, they removed the numbers from the x-axis, so we don't actually know what the real equivalence ratio is. But it's to say they were able to get, you know, on the order of 200 parts per million at atmospheric pressure. Then they have some phase 2 award results that they showed at the meeting, and they showed with a little bit more optimized combustor and operating at 3 bar, they were able to get those NO emissions down to almost 50 parts per million. So that's getting very, very close to what those ideal theoretical models are predicting. So that was very encouraging. And so the last,
it just popped up to give you the 3-minute warning. Okay.
All right, sounds good. Yeah, I'll finish up real quick. Last thing I want to mention is just on oxy-ammonia combustion. There's really not a lot of results out for this. This is some results from a numerical study. You know, they showed minimal NOx effects up to about 30% oxygen, but substantial increases as you went up to 100%. So, you know, getting certainly in the thousands of parts per million, even the tens of thousands of parts per million. Also, just highlight one of the only examples I know of some experimental oxy-ammonia results was from Linde in 2021. And they showed, again, I'm just going to highlight kind of the NO on the right side here. They're looking at stoichiometric ratios. So over here is rich and over here is lean. But again, so for lean conditions in the thousands of parts per million, depending on the amount of ammonia, go into those rich conditions, you know, really help to limit the NO production there. Again, this was a single stage kind of typical combustor, so it might highlight a potential for low NOx if you implemented like an RQL. So just to kind of conclude real quick, you know, the high temperature and pressure of the Haber-Bosch process, I think continues to be a challenge overall for ammonia. Transport and storage really depends on distance. On the combustion side, really just highlighting that model validation is still needed to fully evaluate a lot of these combustion systems, and NOx really remains the biggest challenge. These two-stage strategies have been effective. You know, the models can show sub 50 ppm. That rich stage equivalence ratio is very, very impactful, but we still need more data. So I think for gas turbine applications, we need high pressure data, you know, at above 10 atmospheres. And then to highlight that little testing's been done for the oxy-ammonia stuff. Additionally, I'll say that the applicability of the current kinetic models is probably unknown as well for those oxy-fuel conditions. And then data is needed specifically for furnace applications of ammonia. And so I just have one more slide after this, but I just wanted to highlight, so we have at NETL ongoing fundamental work, and that's really kind of the stuff that I was presenting with the flame images. But I wanted to highlight that we're in the process of expanding our ammonia work. So we're developing a liquid storage facility and kind of scaling up our efforts. We're going to have a high pressure combustor facility that we're modifying for ammonia. We're also working on a dedicated kind of industrial furnace testing facility, kind of in the 2025 timeframe, so a couple years down the line. For hydrogen and ammonia fuels, we should have oxy-combustion capabilities, and the hope here is that this is intended to be kind of a user facility, so we can collaborate with other folks that want to develop these carbon-free technologies. And I just wanted to highlight also that the next ammonia combustion working group meeting is Tuesday, November 7th. So if anyone has interest here, just shoot me an email and I can get you on the distribution list. And with that, I can take any questions.
Okay, thanks very much, Clint. And this was an interesting presentation. I don't think there's been as much attention paid to the potential to use green ammonia as a fuel versus green hydrogen. There's been discussion around green ammonia for transportation, right, from generation or remote places, and generally it's focused on decomposition and use. So I think the work that your team is doing is really interesting and fundamental in this respect. A question on the chat was with respect to the potential for corrosion from ammonia. Is it a big deal, you know, for the systems that you're using, but also in the event of leakage?
That's definitely a good point. So there's a lot of materials materials challenges and things that need to be considered. Even in our small scale experiments, we had to replace a lot of components to make sure they were corrosive compatible, things like flow controllers, valves, etc. So as a drop-in fuel, I agree that that's going to be something that's going to have to be considered. Absolutely.
Okay.
And the fact that it's toxic as well, that's really the kind of a separate, it's not part of the technical combustion challenges, but I think it remains a major challenge and potential barrier, is just the toxic nature of ammonia in general.
Right. And is there anything being done specifically from a research standpoint to address those issues and handling if it becomes more widespread, if there's more widespread uses of fuel?
I think there is. We're not specifically doing any of that work right now. But yeah, I know some other folks are looking at safety aspects, and I think the DOE has interest in considering safety aspects as well.
Of course, that makes sense. Okay, so thank you very much, Clint, for your presentation. And I guess on behalf of both myself and Mike, thanks to all of the presenters for the work they did preparing the material that we reviewed today. At this point, I think we'd like to pass it over to Charlie for a wrap up from AIST.
Ewan and Mike, thank you very much for moderating. Anders, David, Clint, excellent presentations, and we look forward to having more interaction on the decarbonization topic. AIST wants to remind people on how to find the digital recording of this webinar. It's within the same area that allowed you to register, and there are future webinars always available at this area on the website, whether it's past webinars or upcoming webinars. AIST also has in place more than 10,000 downloadable technical reports available through our resource center. And we want to remind you that there are in-person conferences still yet this fall, the last one being the Environmental Solutions in Charleston, South Carolina. We're just finishing up this week the making, shaping, and treating of steel. And our last reminder, this is where you can find future webinars. And we look forward to having everyone consider coming to the May 2024 AIS Tech meeting in Columbus, Ohio. Thank you all for your attendance, and we look forward to seeing you whether in person or virtual at the next AIST event. Thank you all. Have a good day.
Thank you.
Thank you.
Thanks.
Yeah.
Thanks.